close this. So you'll see at the top where it says estimating finite sums. So obviously we know what a sum is. All right, it's the answer to an addition problem. Finite means it actually, what we're adding terminates. It doesn't go on infinitely. It's something we do later. And then what you will hopefully recognize, I know you still do this a little bit in our Math 1, Math 2, and 3, is the sigma notation, this little guy here, the sigma sign. And then what you would notice, I kind of have it all written down. Whatever your lower limit of summation is here, this k, that's the integer that we start at. So if that's like a 1, which I currently have, then we're going to start by plugging in the integer 1. And we continue to plug in every integer until we hit the upper limit, which is whatever that n is. And then what we're plugging that into is what we call the general term, and that's our a sub n. That then produces a sum. The sigma sign is telling us that we're going to be adding all of those terms up. Whatever that answer is going to be our sum. So pretty simple here. We don't deal with this in too much depth because what we need to know is pretty basic. So what this is just saying is our general term is k, our lower limit is a 1. So we're going to start by plugging the integer 1 in for k, which means you just get a 1. Then you're going to plug in every integer up until 4. So we would do plus the next integer of 2, and then the 3, and then the 4. And since 4 is our upper limit, that's where you would stop. Sigma then tells us to add all of those up. When we add all of those up, we should get a 10. So that's the value of that sigma sum. Man, I don't know why it looks like that up there. It looks weird. There. Next one, starting at 1, we're going to plug in every integer from 1 through 3. So we would get 2 to the 1, 2 to the 2. And since our upper limit is 3, when we get to the 2 to the 3, we stop. So that is going to be what? 14. And then the last one, once you're just squaring every integer from 1 through 5. Is that going to give us 55? All right, so easy enough. Sum and difference rules for these. So if we ever have two different sums or two different terms, like let's say we want to add k plus k squared, we could if we want. Actually, I see a little typo here. This is a k squared. Turn this thing into a k squared also. So if I have a binomial and the two terms are being added together, we could if we want. We don't necessarily need to. But as we move throughout the course of this chapter and later chapters, there's going to be opportunities where we want to do this. We could just split that into two separate sums. Find the sum of the k, find that sum of k squared, and then whatever those individual sums are, you would then add together or subtract together, whichever the sign is that you would have had. If I have a constant rule, so this here is our constant, I could if I want, and again, we don't have to, but as we get experience and see different types of problems and the way things get set up, we could, if we want, take this c and just ignore it and find the sum of our general term like we did earlier. And then whatever that gives us, we would just multiply by the multiple of whatever we just pulled out in front. Okay, so we can pull a constant out if we wanted to. And then our constant rule is, if my general term is a constant, so long as I'm starting at 1 right here, then my sum is just the product of whatever that constant term is and whatever that upper limit would be. All right. So we'll do some of those now, starting with the constant rule. So according to our little constant rule right here, this answer has to be 6 times 5, which is 30. If you think about why that is, we should have 5 terms because I'm starting at a 1 and I'm finishing at 5. And then isn't every single one of those terms just the 6? So that's why we really just have 5 6s. So we can just multiply the 5 and 6 together, get our 30. Number 4, what we said we could do. So now, again, we're going to do it now both ways. So you can see that they are equivalent to each other. And then as we move throughout the course of the chapter and later chapters, you'll kind of see when do we want to do one method, when do we want to do the other method. We could split that up. Find the sum of k, find the sum of the two, and then find their difference. We don't have to do that though. So we could have done what we did at the top of the page and just do 1 minus 2, and then plug in the integer 2 minus a 2. and then a 3 minus a 2. Let me go up here, and then a 4 minus 2. So there's nothing stopping us from doing what we did in the first three problems at the top of the page. And this would have given us -1 plus 0 plus 1 plus 2. So these all just kind of cancel. Our answer would be 2. We should get the exact same thing with splitting them into two separate sums and then subtracting them. So for that one, this first one, we would just do 1 plus 2 plus 3 plus 4, because we're plugging in the integers 1 through 4, and our general term is just the k term. Minus, and then we can do our constant rule, right? We can just do 4 times 2, and we can get that one to be an 8. Uh-oh. Yeah, I did that right. So add these up. 4 and 3 is 7, 8, 9, 10. Let's take away the 8. You're going to get your 2 the same way. So no, you can do it either way. Right now, we're just kind of getting exposed to all of this. So you may ask, why would I do one and not the other? We just want to be able to do both, depending on our problem as we move forward. All right, and then 6, one to make you think just a little bit, because these should all be pretty nice. And it also just gets to the point where if I have multiple k's, then when I plug my integer in, I just have to plug it in for everywhere where I have the k. So for this one, I start with the integer 1. So -1 to the 1, cosine of 1 pi. I don't know if I can squeeze this in. Plus -1 squared, cosine of 2 pi. -1 cubed, oh boy, cosine of 3 pi. I can't do it. Plus -1 to the 4th, cosine of 4 pi. It just gets smaller and smaller and smaller. Good little review of some values on the circle that we should know pretty well. So this first term, we're definitely going to get this -1. And then the pi is over here. So the cosine of 1 pi should also be a -1. Plus, and then the -1 gets squared for that next sum, or the next term. So we're going to get a 1. 2 pi is right here. So the x coordinate at 2 pi should also be a +1. -1 cubed is a -1. 3 pi, so this was pi. This is also 3 pi though. The x coordinate over there, -1. And we kind of start to see the little pattern that's happening. -1 to the 4th would be a +1. Not only is this 0 and 2 pi, but it's also 4 pi. So that would have to have a value of 1 also. So all of them give you a 1. Add them all up, should get a 4. All right. And then the last thing that I'd want you to do with regards to the old stuff that hopefully you are recalling now and thinking this is pretty easy, we did this last year, is if I give you the sum, can you write the sigma notation for that? So do that. So do your little sigma sign. See if we now understand all the different elements, lower limit, upper limit, and then what the general term is. All right, Andrew's right in front of me. He threw his pencil down with authority very quickly. So what do you got there, Andrew? Good. Good. So we had 4 terms here. So we started at 1. Upper limit is a 4. That gives us our 4 terms. And then it's just 1 squared, 2 squared, 3 squared, and 4 squared. So we just took his k and he squared it. We can play all kinds of games with this. I mean, there's nothing stopping us from starting that at a 0, a 2, a 3. For the sake of just making this nice and easy and not getting too creative, we're going to start at a 1. All right. Last one, same thing. Go ahead and set all that up. So this one, we said we're going to start at 1 just to make things easy on ourselves. since we have 1, 2, 3, 4, 5 terms, our upper limit better be 5. And then anybody here get this one? Yeah, good. Should be 2K. All right, 2 times 1, 2 times 2, 2 times 3, 4, and 5. That's how we get our 2, 4, 6, 8, and 10. All right. So everything before here, you saw last year or somewhere, Math 1 or Math 2. Just a review, we're going to be using all of those things for what we are now going to do. So now the whole idea of area is the basis of everything that kind of happens in, the B portion of, either Calc AB or for us BC. So it says find the area under a curve, and we're going to do that by using rectangles. Okay. So it says if I give you some function on an interval, closed interval A to B, then when we start talking about the net change in that area under a curve. So if I ever ask you basically to find, the big thing is the area under a curve. If you're asked to just find that, that will always be defined as the region enclosed by the function and the x-axis, and then whatever the vertical lines that would have been created by our limits are. So between A and B, it's always between the curve and the x-axis. If your function extends below the x-axis to indicate that that area lies below the x-axis, it's going to be given a negative value. And then using rectangles allows us for a way to approximate the area underneath a curve. So kind of just a general little sketch to put all that together. Let's say I gave you this and I gave you this as our function. If I ask you to find the area enclosed by the curve, it is the area between the curve and the x-axis. So we'd have this here, and then we would also have this here, assuming that this was A and then this was B. Anything above we consider to be positive. Anything below, we're going to assign a negative value to it. Using rectangles, so now think about what that means. If I could start drawing some rectangles in here, we know how to find the areas of rectangles, so it wouldn't be exact because we're going to lose these little regions. But I could draw some rectangles in here, and then using those rectangles, approximate the area that's going to be underneath our curve, knowing that we're going to lose a little bit of area in this instance, but that's why it's called an approximation, okay? So for us to do this, the rectangle method for approximating the area under a curve, can we still see that? Yeah. So first, number one, it says partition just means break it up, so divide it. So divide the section bounded by what I just drew above, the section bounded by the function, the x-axis between A and B, with subdivisions of rectangles with equal base. So kind of what I did informally up here. We would want all these bases to be equal to each other, and I'm just going to break it up evenly to get all these rectangles. The reason we can use rectangles is because we know how to find the area of a rectangle. That's simple. We've been doing that for a long time. It's our base times our height. Our base, let me draw this in down here a little bit better. So let me draw in a function that looks like this. So this will be f. We'll say this is A, the y-axis, and then we'll say this is B. So what we would do, I'll break it up into two right now. So I'm going to draw two rectangles. So this is me breaking the section bounded by that into subdivisions of equal rectangular bases. And then what I'm telling you is your bases now, so wouldn't these be our bases? Since they lie along the x-axis, your bases would just be whatever the change along the x-axis would be. So I put the little delta x there. It's kind of small for you guys in the room. Whatever that delta x is, that would be the length of our bases. The height of our rectangles, if I put a dot right here and a dot right here, this would give me the height of these two different rectangles, but by putting it on the curve, wouldn't the height of the rectangle really just be the functional value on the curve at whatever x coordinate where I'm hitting the curve? So the functional value, the y value is our height, similar to that optimization word problem that we did in last chapter. And then our base is our change in x. The way we're going to calculate our change in x is this. So the way I can calculate this is what's the difference in the interval? Whatever that is, I'm just going to divide that by the number of rectangles that I tell you to use. Then our rectangles can be inscribed, circumscribed, midpoint, left endpoint, or right endpoint. We're going to get into that next. And then the approximate area underneath the curve is simply the sum, that's why we did the sigma stuff at the top of the page, of those areas of each rectangle. All right. So that then takes us to the next page, where we're now going to put those two ideas together. So if you notice, here's our sigma sign. So we're going to be finding a sum. We're going to start at 1. This would tell us how many rectangles we have. The n stands for the number of rectangles, because that's how many terms we'd be adding up. And then all this really is, the delta x is our base, and then whatever the functional value is on the curve is our height. So all we are really doing is adding up the areas of rectangles, or heights times our bases, with just some fancier notations. All right. So first, let's make sure we understand what all these types of rectangles are indicating. So what I want you to do underneath inscribe. So draw in just kind of a first quadrant and draw in a function that looks like this. And then let's say that A is at the beginning and we'll go to B right here. What I'm going to have you do is cut that in half and then cut each of those in half. So what we end up with is 4 bases. So here's 1, 2, 3, the bases of 4 different rectangles. So inscribe basically describes what we're going to try and draw in. We're going to draw in rectangles that are, if we think about this prefix, inside of that curve exclusively. So what I would do is for an inscribe, I'm going to go up from here, make a big dot on that curve. I'm going to come over and I have my first rectangle. It's inscribed because it's touching the curve, but it stays inside of it the rest of the way. If I continue to just do that pattern, go up from the right, or sorry, up to the left, move to the right, I get 4 what we would call inscribed rectangles. The dots that I'm putting here nice and big, those are important. That's how we're going to find our height in a little bit when we actually do a problem. Whatever the y coordinate on the curve is the height of those 4 different rectangles. So those are inscribed. For circumscribed, start out the same way. Not every graph's going to look like this, but just so we can compare. Draw in what's pretty much the same thing. We'll put B here again and then A here. Cut those intervals in half and then cut each of those in half further. So now if I start to draw in rectangles here, so here's 1, 2, 3, here's the makings of my 4 rectangles. If I want to now be circumscribed, we want to go outside the curve. So I want to go up from the right side, touch the curve, and then cover that first interval by moving to the left. Go up from the right, move to the left, and we still get 4 rectangles, but these are what we would call circumscribed. So a question that's definitely going to pop up in due time. If I were to ask you about inscribed, at least for this graph, seeing how we're concave up or increasing, if I ask you if we're over or under approximating the real area, would we all agree that that is under approximating the actual area? Because we're losing these little triangular regions here. But if we know that, then that actually helps us because we know our real value would be a little bit more. If we go to circumscribe, now these rectangles are accumulating a little extra outside of the curve, so we know that approximation would be a little bit bigger than the real area. All right, next one. Mine and what will be your least favorite one are the midpoints. So you're going to draw A here and then B there. Start it out the same, cut it in half, and then cut each of those in half. If you look at the inscribed, notice how each rectangle is hitting on the left endpoint of our rectangles. On the circumscribed, we're hitting each rectangle on the curve at the right endpoint. What midpoint means is if I go to start to sketch my 4 rectangles in, so here's 1, 2, 3, and 4, so the same thing we would have gotten before. We don't want to touch the curve on the left. We don't want to touch the curve on the right. We're actually going to go up from the middle, put our dot. So a little bit of the rectangle goes outside the curve. The other half is going to go underneath the curve. So same thing for number 2. Go up from the middle, give the curve a little kiss, and then move left, and then move right. So then hopefully we're thinking, all right, like if the first one over approximates, the first one under approximates, the second one is going to over approximate. It's kind of hard to tell which one this does. However, we should understand that this one is much more accurate than the previous couple, correct? Because you're going to gain a little bit on one side, you're going to give it back on the other. That is actually a really good approximation for how much area would be underneath the curve, the midpoints. But they're also the biggest pain to do. Left endpoint, do not draw the same graph in. So now draw in, I want a first and second quadrant. So now draw in a parabola that looks like this. Put A over here and then B over here. We are going to cut that in half though, so the y-axis would cut it in half. And then cut each of those in half. So we're still going to go with 4. We don't always get 4, but just for the sake of comparison, I want these to be somewhat similar. When it's left endpoint, that just means we've already done left endpoints a little bit, and then right endpoints and then midpoints. You have to hit the curve with these 4 rectangles on the left side every time. So for rectangle number 1, we have to go up from the left side, touch the curve, and then cover that first interval by going from left to right. Same with rectangle number 2. So here's its base. So we have to go up from the left. Again, give the curve a little kiss and then move to the right here. And then right now you're thinking, all right, well, aren't these really just circumscribed rectangles? Why are they given a different name? And that is because as we now go to that third rectangle, I have to go up from the left. Once I get to the curve, we touch it and we immediately move to the right to cover the next interval. Notice how that one is no longer circumscribed. Now that's inscribed. Okay. So now for 4, same thing. We're going to go up, hit the curve. So we don't care if they go outside the curve or inside of the curve. We just have to hit with our left endpoint at all times. All right. And then last but not least, you can probably anticipate what this one's going to look like. Draw in the same one that we just drew before. Draw in the full parabola on the first and second quadrants. Cut it in half. Here's 1, 2, 3, 4 different bases for our 4 rectangles. Now we're committed to hitting it on the right endpoint every time. So for rectangle number 1, we got to hit on the right side. For rectangle number 2, I'm going up from the right, hitting the curve, move to the right. So now those are our inscribed rectangles. But as we move to this third rectangle, when I go from right to left, we go outside of the curve. And we don't care. We just know we're always hitting with our right endpoint. These are all used interchangeably. There's not one that gets used more than the other. So we just want to be able to work with all of them and know what each one of them looks like. Some of them will over approximate, some under approximate. I'll ask you about which ones are the most accurate. So the graph to start all these off is a nice visual. All right, what do we got? Okay, looks like we got time to get one of these done. All right, and then I've talked about it. Notice where the point that's hitting the curve every time. That's how we're going to be able to figure out what our height of all these rectangles is. This big red dot that I keep putting, whatever the y coordinate of those points are, that's the height of each rectangle. Okay. Okay, so let's do one of these. Hopefully we can get through one. Write a Riemann sum. So a Riemann sum is a sigma notation that's finding the area underneath our curve. Okay. Then you're going to find the area underneath this curve on the interval of 1 to 3 with n equals 4 inscribed rectangles. So as best I could, I actually gave you one that's going to look like the ones we drew at the top here, so we don't get too crazy too soon. So we really just need to give yourself some room to operate. So this doesn't have to be to scale. So go from 1 to 3. Our parabola is x squared plus 2, so we have a y-intercept of 2. We don't really need anything over here because we're only staying from 1 to 3. But over here should look basically like a bunch of the ones that we drew at the top of the page. And what we're going to do is approximate how much area lies in between 1 and 3. Notice how it's a curve, even though I drew mine kind of flat. So it's not some geometric shape that we can just find the area of. It somewhat looks like a trapezoid, but it's more curved than I probably indicated. So it's not a trapezoid. So in order to find this area, we're going to use rectangles. So what I am then telling you is, and again, this is x squared plus 2. We're going to go from 1 to 3. We want 4 rectangles. So what we now need to know, so let's split this up first, because it's going to look like the ones above. When we draw all these rectangles in, so here's our 4 bases. So here's rectangle number 1, 2, 3, and then 4. What we want to know is what's the length of each base. So on the previous page, we said the way we can calculate that change in x is by doing the difference in the interval. So we want to go from 1 to 3. So we're covering an interval of 2. And we're going to do it in 4 steps. So what that then tells us is we're going to move over by a half each time. So then that means that this x value is 3 halves. This would be 2. This would be 5 halves. And then we finish at 3. Real quick, just to make sure we understood what we did just above here. Draw in now 4 inscribed rectangles, just to make sure we understood what we did right above this. So now draw those 4 rectangles in, make sure they are all inscribed. All right, to keep them inscribed, you should have been using the left endpoint the whole time, correct? So I could have said left endpoint also, and they would look the exact same in this case. So we would have touched here, moved to the right, here, here, and then here. So I'm making big fat red dots here. Those are important. What we're then going to do is list those values. So the place where we hit the x coordinate are at 1, 3 halves, 2, and then 5 halves. So you're going to want to list those. And then here's where things get just a little bit weird. Even though these are x coordinates, we're going to call this C sub 1, C sub 2, C sub 3, and then C sub 4. And I'll explain why here in a minute. We're kind of ready. We're going to set up our sigma sign. Let me leave a little room to operate because this gets a little messy. So we're going to set up our now sigma, and I'm going to put k equals 1 in our denominator, or in our lower limit, and then 4 for our upper limit, because we're going to have 4 rectangles to add up. All we are doing is doing our height times our base. Well, our base, don't we know our base is always this 1/2 up here? So we're going to put a 1/2 here. We're basically coming up with our own general term. And then I need to multiply by my height. I've mentioned it a few times. Isn't the height just the y coordinate on the curve? So the curve gives us our height. So where this now gets a little bit different. So here's where I want to be careful. It's very tempting, and eventually I actually do kind of cheat later in the year, to put x squared plus 2, because that's what the functional value is. But recall what we did at the beginning of the class. Don't change yours. But if I did this here, don't I have to plug in only the integers 1, 2, 3, and 4 into here if I did that? We don't want to plug in those integers. We want to be plugging in these values right here, because these are the x coordinates that we're going to use to figure out what our heights are. So the way this gets written, instead of x squared plus 2, we're going to get rid of the x, and we are calling this c sub k squared plus 2. That's why if you look at the top of your page, let me pull this up. Notice how this is not f of x. This is called f of c sub k. All right, so just a little change in notation. And here's why we want to now write it like that. If we do what we did at the beginning of the class, and what you did last year, what we know, this will erase, we know we have to plug in now the integers starting at 1. So let's plug in the first one. So that means over here, find where k is, and the k is the subscript. So I would now get c sub 1 squared plus 2. And then I'm going to multiply that by my base, which is 1/2. Now, Long term, we're not putting C sub 1 because what do we know C sub 1 is? 1, right? So it really is just those x coordinates. So we're just going to plug in A1 because that's what the C sub 1 is on this one. Plus, if we go to the next one, we have to plug in the integer 2. So we technically would get C sub 2. I don't know why I'm writing so small. This is not going to fit anyway. So you're going to do C sub 2 squared plus 2, and then times that 1/2. But don't be silly and actually put C sub 2, put what we know C sub 2 is equivalent to, and C sub 2 is this 3/2. Plus, next would be C sub 3, so 2 squared plus 2 times the 1/2, and then I ran out of room as I was afraid of. Let me see if I got more room over here. Actually, I do. Perfect. Plus, C sub 4 would have been 5/2 squared plus 2, and then times 1/2. Every single one of these, all we are doing is taking the height times the base. So this right here, this is going to give us the area of rectangle number 1. This would have given us the area of rectangle number 2, number 3, and number 4. And then when we add them all up, that should give us that overall area, at least as an approximation. Here is typically, and we're a little low on time here, and it's kind of probably a good place to stop, but have a method for plugging all of these in. Some kids over the years, they just plug this in and then they write that answer here. They plug in this one individually, write that in. They do these all individually and then add them all up at the end. Some people who are a bit cocky and arrogant with their calculators say, I can do all that at once. And they just throw this big thing in there all at once and hit enter one time. But whatever those now all add up to equal, that is your answer. All right. That should give us 10.75. I'll show you the real area tomorrow. I'm afraid to pull up my calculator right now because it's the end and it a lot of times freezes. But what we would then know is, if this is the approximation, wouldn't we then know that our area is just a little bit more than that? Because aren't we losing these little regions in here in our approximation? So it's reasonable to say 11, 12-ish would be our area. Okay. Whew. All right. We okay with that? Makes sense, hopefully? Yeah, Naren? If it was inscribed and I had you come over here, then yeah, you're gonna have to start doing some right endpoints over on that side. Yep. And we'll see one of those here in a little bit. Okay. All right, we're less than a minute. So have a good weekend. We'll see everybody on Monday, Monday. All right, and then just bring this. We'll finish this off. All right, we'll see you guys.